I'm Kent Dickens, and I will be presenting with my colleague, Dr. Ing Tan. We're with HDR and are actually located in the Raleigh, North Carolina office. And while we are sad to not be giving this presentation to everyone here in person, we are thrilled to be sharing this project with you. As Ben already stated, the title of the presentation is definitely a mouthful, so we'll just jump right in. The bridge is located in downtown Cleveland and was showing signs of distress. The Greater Cleveland Regional Transit Authority, or GCRTA, was concerned that this distress was a symptom of the bridge not behaving consistently with the original analysis. GCRTA prepared an innovative scope of work, which included a detailed inspection and instrumentation plan, the calibration of 3D finite element models, and analysis of the structure. Ing and I were fortunate enough to be a part of the project team and were tasked with the calibration of the models and analysis of the structure. In addition to key staff from GCRTA and HDR, we partnered with Dr. Rob Connor and Dr. Francisco Bonachera of Purdue University, who carried out the instrumentation and data gathering. The agenda for this presentation will roughly follow the scope of work for the project. We'll give an overview of the structure, take you through some highlights from the inspection report, and describe the instrumentation plan. We'll also review the basic concepts of rail structure interaction, or RSI, and take you through the calibration study. Finally, we'll conclude with key takeaways from our analysis. Let's begin with a look at the basic characteristics of the bridge. The bridge was built in 1996. It is a 5-span continuous superstructure with an overall length of 645 feet. There are reverse curves on the bridge with a 300-foot radius curve at the beginning and a very tight 140-foot radius curve at the end. There are fixed pot bearings at piers 3 and 4. All other bearings are guided sliding pot bearings. There are 2 bearings per support, and they are placed along a skew represented by the red lines on the image shown here. The bridge utilizes a single cell box girder with precast segments and was built through balanced cantilever construction. Post-tensioning is provided by bonded strands in the top and bottom slabs. The bridge carries 2 tracks of light rail transit traffic. The track is built using continuously welded rail, which does not have any expansion joints, meaning that the thermal strains in the rails must be relieved through expansion and contraction in the curves of the track. The rails are fixed directly to the bridge by thousands of individual rail fasteners. These fasteners allow for longitudinal movement, but not transverse movement. So now that we know some of the basic characteristics of the structure, we'll walk you through the signs of distress that caused us to target RSI as the likely cause. And we'll also talk about how we designed the instrumentation plan to capture the data needed for the calibration study. Let's look at the effect that rail structure interaction has on the bridge. The animation shows the effect of thermal contraction of the rails, pulling the bridge to the inside of the curves, resulting in plan view rotation of the entire structure. Distress due to this transverse movement of the rails was evident during the inspection. There was cracking in the bridge around the rail fasteners, cupping of ballast just off the structure, and damage to the rail fasteners attached to the abutment back wall. These are classic signs of RSI effects. So after observing the distress to the structure and determining the likely cause to be the thermal effects from RSI, we created a plan to capture the appropriate thermal and displacement data for calibrating our finite element models. The temperature data was taken continuously over a 2.5-month period. There was 1 sensor to measure the ambient temperature located under the box, and there were 3 sensors embedded at various locations along the height of the box to measure the temperature of the concrete. There was also 1 sensor embedded in the rail. 2 displacement sensors were placed near the expansion joint at the beginning of the bridge. This picture shows the abutment 1 displacement sensor, which measured relative displacement between the box and the abutment. The Rail 1 sensor was placed on the bridge deck directly above the abutment and measured the relative displacement between the box and the rail. The displacement data was recorded over the same monitoring period as the temperature data. So now that we have introduced some RSI effects and their driving factors, I'm going to hand it over to Ing to review the basic concepts of RSI and share how we used the thermal and displacement data to calibrate the models to accurately capture these RSI effects.
Thanks, Kent. Next, we are going to explore a fascinating topic, marriage, a force marriage, that is rail structure interaction. What is rail structure interaction? Let's look at this picture. In this picture, it shows the superstructure. The 4 green lines represent 4 rails. The diamond shapes are individual rail fasteners. The rail and the structure have different exposure conditions, and the rail heats and cools faster than the massive concrete structure. So they are subject to different thermal effects. However, they cannot respond to the thermal loads independently because the rail fastener ties them together. The complex nonlinear interaction of the rail and the structure under temperature change is called RSI. To keep it simple, RSI is a force marriage, and it could be really stressful. Just like any relationship, if we don't take good care of it in design, the structure could crack and the rail could break. Well, you may ask, if we get a transit bridge, when should we consider the rail structure interaction? Let's go back to this picture. Do you see these 2 key elements? The first element is the continuous welded rail. The second element is the relaxation track. When we see this combination, welcome to join the RSI club. We just briefly touched on the overview of rail structure interaction. Let's move on to the calibration study. This is the RSI model that we use to do the study. There are 3 stars in the calibration study: fastener properties, initial conditions of the fasteners, and temperature load. So it is FIT, fit. Let's meet them one by one. First is F, fastener properties. The fastener holds the rail in place through friction. Once the clamping force is overcome, the fastener starts to slip. That leads to the next question. What is the clamping force? We pick 2.4 kip per fastener as a starting point to do the calibration, because that value is fairly close to what we have seen in test. We model the fastener as a hysterectic spring. After many trials and errors, we found that 1 kip per fastener gives better correlation in our case. Second is I, initial conditions of the rail fastener. It is important to recognize that there are thousands of fasteners, and after 23 years in service, the fasteners have gone through so many loading and unloading cycles. Let's look at this graph and imagine. At the very moment that we start gathering data, we told the fasteners, hey guys, please don't move. We want to know where you are along this curve. Just like the colorful dots in this graph, they are at different stages along the curve. That's the initial condition of the fastener that we are talking about. Last but not least is T, temperature. Temperature was recorded every hour for 75 days. I invite you to look at this table and compare the maximum and minimum temperatures of the rail and the superstructure. This is very interesting. The test data shows that in this 75-day period, the maximum and minimum temperature occurs within 5 days as shown in the graph below. In this graph, the green line represents rail temperature. The red line is superstructure temperature. On day 1, the rail dipped down to -2 degrees. Then on day 5, it went up to 80 degrees. In our study, we used temperature change every 2 hours as uniform temperature loads and ran the analysis in 900 stages to cover the 75 days. We have just met the 3 stars FIT. Let's move on. and look at the calibration study. We are going to use 3 slides to show the calibration. In these slides, the horizontal axis represents the monitoring period. The vertical axis represents displacement. On this slide is longitudinal displacement between abutment 1 and deck. The abutment doesn't move. So in other words, this displacement is the bridge end movement subject to temperature change. Before we look into the curves, let's imagine 4 rails resting on the massive concrete box and compare the stiffness of the rail and the box. The rails are just like noodles. So theoretically, the rail should have negligible effect on the bridge end movement under thermal load. That is exactly what this chart shows. The red line represents using 2.4 kip per fastener. The yellow line is using 1 kip per fastener. They are almost overlap. Next, let's turn to the longitudinal displacement between the rail and top of deck. Now the rail fastener effects kick in. The green line is test data. The yellow line is using 1 kip per fastener. The red line is using 2.4 kip per fastener. 1 kip per fastener gives better correlation to the test data than 2.4 kip per fastener. Again, this bridge has been in service for 23 years. There are cracks in the plinths. The clamping of fasteners get loose, so lower value makes sense. How about the effect of the initial conditions of the fasteners? The yellow line assumes all the fasteners start from 0 displacement, which means each one has to overcome the fastener clamping force before slipping. The red line assumes the fasteners have been engaged, and lots of them have already on the slipping plateau. So the red line gives higher displacement than the yellow line. This project not only demonstrates finite element analysis of RSI, but also has some test data to validate the analysis approach. In the industry, rail structure interaction test data is very limited, which makes this project even more valuable. I would like to use these 3 takeaways to wrap up this section. In RSI analysis, the fastener properties are not overly sensitive. The initial conditions of the fastener could play a significant role in RSI. Uniform temperature load is the driver. Now let me hand it over to Ken.
Thanks, Ing. So now with our models calibrated, let's look at some key results. Here's a basic sensitivity study we completed to bound the effects of RSI. This graph shows the stress in the top right corner of the box for the envelope of uniform temperature rise and fall. Negative values represent compression, and positive values represent tension. The stress is plotted along the length of the structure, with vertical lines representing each abutment or pier. The green line represents the stress without consideration of RSI. The yellow line represents the stress considering RSI with a 1 kip per fastener yield plateau, which is the calibrated value for our bridge. The red line represents the stress considering RSI with a 2.4 kip per fastener yield plateau. What becomes apparent from this stress plot is that there is a significant difference between stresses when RSI is considered versus when it is not, and that it is the mere consideration of RSI that has the greatest effect on the state of stress, and not the rail fastener spring properties themselves. Another important takeaway is the influence of the plan view curvature on the state of stress. The tangent portion of the track between piers 3 and 4 does not show a dramatic effect from RSI. The 300-foot radius curve at the beginning of the bridge shows a distinct effect from RSI, but it is really pronounced at the end of the bridge with the very tight 140-foot radius curve. This plot shows stresses factored for the AASHTO LRFD Service 3 limit state. The stress is, again, taken in the top right corner of the box, with negative values representing compression and positive values representing tension. The blue line represents the stresses from permanent loads. The stresses are compressive and follow a fairly symmetric pattern along the bridge. The green line represents the stress envelope of live load plus impact. These stresses also follow a fairly symmetric pattern along the bridge. The yellow line represents the stress envelope of uniform temperature rise and fall from the calibrated RSI model. These stresses do not follow a symmetric pattern along the bridge, as they are heavily influenced by the plan view curvature, as discussed previously. The variance in magnitude of the uniform temperature stresses is significant. Within the tangent section between piers 3 and 4, the uniform temperature stresses are minor in comparison to permanent load and live load effects. But at the end of the bridge, with the tight radius curve, the uniform temperature stresses are larger than the live load stresses. The influence that RSI effects have over the state of stress is significant for this structure and is certainly a key cause of distress noted in the inspection report. So to recap the major takeaways from our analysis, RSI effects are greatest for uniform temperature loadings. RSI effects increase in tighter curves. RSI stresses can be significant and should certainly be included in the analysis of any structure with direct fixation track on continuously welded rails. This was a true team effort led by a forward-thinking client, and we feel very fortunate to have been a part of it. The data gathered from the instrumentation plan was used in the calibration study to determine the rail fastener properties specific to this bridge. The calibrated models were then used to analyze the structure and quantify the effects of RSI. While we did tailor our analysis to this specific structure, we hope that you are left with a better understanding of the basic mechanics of RSI and the importance of considering it during analysis.